think of this as basically, if you think of what I've drawn here, ky can be thought of as a tuning parameter, and then the 2D system described by the kx, kz grow on then goes through a phase transition at each of these while nodes where a certain number jumps. And so there's a lot of recent excitement because after a long search in a lot of different proposed materials, we have RPES data that seems to suggest that we've seen wild semimetals in this material that sort of supported wild semimetals in this tantalum arsenide. And I've shown you RPES data from two groups that came out very recently, including this one, which I think in Science last week. And there are now other examples often coming online. There's another related material, which is a topological Dirac semimetal. And so the Dirac semimetal is to be thought of as a pair of wild nodes that are at the same point that then naively would say that if you have a pair of wild nodes at a single point, this nice protection that you wrote down that you could never gap it out because of the fact that you used all three Pauli matrices no longer applies, because you can now in this 4x4 space you could write something that allows you to mix the two bands and then gap out the wild nodes. So mathematically you would say that a 2x2 mass matrix is impossible, but a 4x4 mass matrix would be allowed. But you might ask if there are other crystal symmetries in the problem. For instance, if there's some kind of reflection or rotation symmetry, you might ask if that crystal symmetry could forbid that mass term. So you wanted to write down a term that mixes the two wild nodes, but if you did that, you'd actually be mixing different crystal symmetry sectors, and that would be forbidden as long as you preserve some crystalline point of symmetry. And it turns out you can, in fact, construct examples of this. Shi Dai and other collaborators proposed some of these in two materials, sodium bismuth and cadmium arsenide. And it turns out these sodium bismuth is a little harder to work with because while it's stable, it tends to explode a lot. So experimentalists don't necessarily want to use that for all their experiments, but there have been pretty great experiments with sodium bismuth already. And the other one is a little interesting. This cadmium arsenide material is a semiconductor that's been around for a while. It's actually known to have very high mobility. It's stable. People make devices out of it. There are groups around the world that work with this. And people have done RPES, so I'm showing the first RPES data on these where they've seen the physics of both Dirac points in both these materials from RPES. And there have been other transport measurements that I'll comment on as I go through. And so a lot of what we say can be adapted to Dirac semimetals, but it's always useful to have the wild semimetal as a toy model because sort of that's the minimal picture. And then to add on the physics of the Dirac semimetal, we have to think a little bit about what survives once you have this additional requirement of a crystalline point group system. So as I said, I'm just going to think of Dirac semimetals for my talk. There's just going to be two copies of the wild semimetal. That allows me to not spend a lot of time on these for the moment and just think about the wild semimetal and talk about the physics there, and then sort of talk about what changes when it goes to wild semimetal. So Dirac semimetal. So the bulk of my talk is going to be about how one would try to detect these topological semimetals. So I want to talk about, suppose I handed you a chunk of material that I claim is a topological semimetal. What experiment could you do to check whether that's a topological state? So one thing you can ask is, there are two pieces there. There's topological and there's semimetal. And the semimetallic feature has to do with the fact that there's a band touching that's described by this linear dispersion. So the first thing you can do is something very nice. You can just say, what kind of resistivity could we expect if we were in the fortunate situation where the chemical potential is exactly at the node? And it turns out that there, because you don't have any scale in the problem, because you have this gap with points, you can get a resistivity that's essentially quantum critical and ignoring logarithms. Up to logarithms, you find that the resistivity scale, the resistivity diverges as the power of the temperature, diverges as 1 over T as equals to temperatures. You can actually do more work to get some more careful calculation, but there's a back-of-the-envelope calculation that's basically a dimensional analysis argument that gives you this. So, like any good back-of-the-envelope calculation, first we have to have an envelope. And now, we're just talking about the DC resistivity here. So the basic idea is that I can write the DC resistivity as just something that depends on the density of states and the diffusion constant. And the density of states of a wild semimetal, if the temperature is the only scale of the problem and I have linear dispersion, essentially dimensional analysis tells you the density of states scales as T squared. The diffusion constant is a little bit more subtle because you need to know a little bit about the scattering of the problem. You need to know about the relaxation rate, or relaxation time. But that scattering, you can get that from a scattering rate. If you assume Coulomb physics, you can extract a scattering rate that basically depends on some fine structure constant in the system, because it looks like just 3D electrodynamics, and goes with 1 power of the temperature. Again, this follows by dimensional analysis, since temperature is the only scale of the problem. And if you put this all together, you get this power law equation for temperature. have just to check whether you have this direct semi-metallic dispersion or in what regime you're in. Then you expect that this would work whenever the temperature was high or large compared to the chemical potential of the system. That's sort of the scaling. Once you start getting to T or more than the chemical potential, if you're away from the node, you'll see corrections to this because you have a Fermi surface. So this is not particularly, this is interesting, but it's not particularly exciting because it's not obviously topological anyway. So for the rest of the talk, I want to focus on topological aspects of these direct semimetals, while direct semimetals and how they show up in transport. So let me remind you of the situation that understands the topological insulators, because it's sort of our first intuition now to go with from there. So with topological insulators, I have both a boundary and a bulk signature of the topology. On the boundary of a topological insulator, I have a protected 2D Dirac surface space that's been seen in ARPES and SPM and sort of signatures of surface transport. And in the bulk, I have a more subtle signature, which is the bulk magnetoelectric effect. The fact that the effective electrodynamics of the bulk has this theta E dot B term. Alpha virtually. But basically, there are these bulk and boundary terms, both of which are different manifestations of the topology of the system. So what I'd like to think about is talking about the topological signatures of these vial semimetals. I want to think about the boundary and the bulk signatures of that. And the boundary signatures I'm not going to touch upon very much in this talk, but I'll just explain their origin just to be complete. The boundary signatures come from fermions, and these things have seen in ARPES, possibly in quantum oscillations. Andrew will tell us a lot more about that in the next talk. The bulk signature there are two kind of bulk signatures you can expect. One of them is a particular kind of quantum anomalous Hall effect of the bulk. And the focus of much of this talk is something called the Adler-Bell-Tschicki anomaly, and I'll talk a lot about that in the balance of the talk. But before that, let me just mention what these fermions are. So I'll remind you that the simplest example of a wild semimetal is you have two wild nodes. The wild nodes are separated from the bulk across the 2 points of the bulk, they're separated. And let's imagine I take a slice through the Brillouin zone between the two wild nodes. Every time a 2D slice in the Brillouin zone, I can take a 2D slice through the Brillouin zone, which has this quantum anomalous Hall effect, where if I take that 2D slice and integrate the Berry curvature across the slice, then I get a non-zero Chern number. Every time I do that, if I look on the surface, you'll find that the surface Brillouin zone of that system and along that projection will have a chiral surface state. And you can think of this chiral surface state as just being the edge state of that 2D Chern insulator. Now, if you take a finite slab in this picture, a finite slab in the Z direction, you'd find one half of the legal 2D Fermi surface on the top, with the other half on the bottom surface. The picture is that you have a top surface of the slab that has something that looks like a Fermi arc, because it looks like the electron just disappears into nothing. Whereas at the bottom you have a Fermi arc that does the opposite. And together they form a legal 2D Fermi surface. And Andrew will spend a lot more time discussing this, because one way you can see the Fermi arcs is in ARPES, which is what I showed you earlier. So these are the Fermi arcs in that example of tantalum arsenide. A little bit harder to see here in the physics of bismuth. But one thing you can see that is seeing Fermi arcs in transport is a subtle thing. And especially in the Dirac case, so the wild semimetal case, looking at one surface, you see electronic dispersion that just ends in a point and doesn't seem to go anywhere. And you can actually check where you can actually change the energy of the incident electron and ask how these arcs disperse. So you might worry that this might be just a Fermi pocket of some kind. But the way you can argue that it's not a pocket is you can just see that as you change the energy, you'll see that all these energy levels shift the same direction, whereas in a pocket they'd have to shift in opposite directions. So you can actually do that for the wild semimetals, but for the Dirac semimetals, it's much harder to check that you've got this physics of Fermi arcs, because you actually have, in some sense, you have two Fermi arcs on the surface, and the signature is really that where they meet at a point that's got a derivative singularity, and that's much harder to make out from the data. But fortunately, there's a much nicer and cleaner signature that I'm just going to talk about in the next talk, which has to do with semi-classical orbits with non-local permutation. Or I'm not going to say much about it, except to say that there's many ways you might see that semi-classical orbit. One of them is quantum oscillation, which Andrew's going to talk about. The other one might be is that something that we're going to work in collaboration with Yuval Baum, mostly, who did the heavy lifting, the student at the Weizmann Institute, but also Eresberg and Adi Stern, is that these Fermi arc orbits can give you an unusual AC electromagnetic response by an analog of something that, it's in some back chapter of Ashcroft and Mermin, something called the Oslo-Connor cyclotron resonance, a particular variation of the cyclotron resonance phenomenon. So let me now focus on bulk signatures of the chiral anomaly, of the topological semimetal. So the bulk signature is, one bulk signature is the quantized anomalous Hall conductivity that was worked out by various people. I think that sort of one of the people here in the room